What's up, guys? Welcome back to Speed, Math, and CS. So today we are going to be continuing our study of AP Physics C, Electricity, and Magnetism, right? Here at Speed, we do AP tutoring, Math tutoring, CS tutoring, you name it, we do most of the things, right? And today we are bringing you Unit 2 of this course, which will be Infinite Charge Distributions and Charge Density. So today we'll actually start using some calculus in order to calculate infinite charge distributions. Remember, the key word here is infinite. That is a sign where we use calculus to solve things, right? So first things first, let's start with a little bit of review from last time, right? So previously we've covered a total of, I'd say, 4 equations last time, right? Where the first two are our golden equations, right? So the first one is that force equals to charge times electric field, and the second one being that work equals to charge times potential, right? So this allows you to essentially get two forms of a scalar, right? Or actually, in this case, force is a vector, sorry. So yeah, both these are vectors, right? So it basically allows you to convert electric field and potential into some units that we commonly use. And in fact, this can be rewritten using the U for potential energy, but it essentially works out the same, right? And then the third equation we went over was Coulomb's law, right? So of course there were several variations to this equation, right? So, but first let's go over just straight Coulomb's law. So firstly, Coulomb's law states that the force between 2 point charges is equal to the Coulomb constant times Q1 times Q2 over R squared. This right here is Coulomb's law. Remember that this K on the AP test, write this K as 1 over 4 pi E naught, where E naught is the permittivity of space, of free space. So, of course, this Coulomb's law equation had several variations, and a couple of these variations stemmed from, first was our potential energy, which essentially stated that potential energy equals to the Coulomb constant times Q1 times Q2 over distance r, right? And then another variation of this was now with potential, right? Where potential equals to the Coulomb constant times Q1 over distance. And then our last variation was for electric field, where electric field equals to the Coulomb constant times Q1 over R squared, right? So you can see with this that for each one of these, we are like taking the original Coulomb's law equation and we are essentially omitting one of the variables, right? So whether that be one of the distances or one of the charges, we essentially omit it to get one of these variations. And the best way you can remember this is by unit analysis, which is another topic we covered last time, right? So notice that force is in newtons, right? Potential energy or electric potential energy or work is in joules, which equals to newtons times meters, right? So the meters in the numerator essentially set from the original Coulomb's law formula, distance or the meters was in the denominator. So this essentially means we omitted one of the distances from the denominator. And then if you look at here, volt or potential is in the units of volts, which are equal to joules divided by coulombs, which are also equal to newtons times meters divided by charge, right? And we can see here, we omitted meters from the denominator, and we also omitted a charge from the numerator. And for both potential and electric field, this makes sense because we typically only refer to one charge and a small positive test charge when we go to calculate either one of these, and then we use superposition to determine its overall sort of electric field or potential for all the charges, right? We simply add them up with like E1, E2, E3, so on and so forth. And we covered this last time, so make sure to check out the last video if you haven't already. So going to the electric field unit analysis, right? Electric field essentially is in units of newtons divided by coulombs, right? And we can see that we omitted a coulombs from the top, and that's it. So, and then finally, we had one last equation, right? So this last equation, right, we'll call this number 4, right? This would essentially relate potential and electric field together, right? So potential, right? So electric field is equal to negative derivative of potential with respect to distance, right? And essentially this is going from electric field to potential, right? So sorry. So yeah, this is going from electric field to potential. So as you can see here, if we have the potential, it is super easy to calculate the electric field because all we do is just take the derivative with respect to R and then negate it. And then we have our electric field. But we'll notice that going backwards is actually a more complicated process and involves integrals, right? This should be pretty obvious why it should involve integrals. But going back, essentially another variation of this equation, right, is that delta V, right, remember change in potential, which is equal to essentially VB minus VA, right? So the potential at point B minus the potential at point A, this is essentially equal to negative integral from A to B of electric field times dr. And you can see pretty easily here why this can get complicated sometimes. Because if the electric field isn't constant, you can't take it out from the integral. So then this process becomes much harder. You have to basically convert the electric field to a function of R. And for that very reason, as we'll see today when we do continuous charge distributions, it's much easier to just calculate the potential and then get an equation for the potential in terms of distance and differentiate it to get the electric field equation versus having to calculate the electric field manually. So now let's try some practice problems using these. So yeah, these are using our two golden equations, our Coulomb's law and all its variants, and electric field to potential equation. So, our first question will be, what potential energy? So let's say we have 2 points here, point A, point B, right? And then at point A, we have a charge of 100 coulombs. And essentially 100 coulombs is pretty big. I understand that, right? But just for the context of the problem, that's the value we're going to be using. And let's say the potential at point A is 300 volts, and the potential at B is 100 volts. So how much potential energy is required how much potential energy is acquired on this charge when it moves from point A to point B, right? This will be our first problem. So right away, you should notice that we are going to be using our second golden equation for this problem, right? If we remember, golden equation number 2, work equals to QV. Because in this case, we're dealing with potential and we have to get electric potential energy. So we're going to actually be using the variation here, U equals to QV. And in fact, because this problem, you'll notice, right, it's talking about how much potential energy is gained when you go from A to B. So we're gonna actually have to make, actually it's not on the screen. So yeah, so we're gonna have to make another variation to this equation, but this one is more simpler, right? Essentially, we'll say that delta U, right? Yeah, delta U equals to charge times delta V. And then essentially we can literally just plug at this point, right? So going from A to B is a negative 200 volt drop, right? So we'll start by saying, okay, change in potential energy equals to the charge, right? Which is 100 coulombs multiplied by the electric potential energy difference, which will be negative 200 volts. That's the amount it loses, right? So the change in electric potential energy will be equal to negative 20,000. Actually, is that the camera? Sorry. Negative 20,000 joules. Yeah, joules. So yeah, joule simplifies to Newton meters. So that's our first practice problem. Now let's go over another problem, right? So for our second problem, right, we'll say, okay, we'll do a similar type problem, right? So we'll have points again, right? Point A, point B, and let's say that the electric field, let's say that the electric field in this region is equal to 300 newtons per coulomb. So essentially, let's calculate, and then yeah, let's say we have this time. Let's do 100 micro coulomb charge. All right, that's the unit for microcoulombs. How much force is required to push this charge over to point B? That's going to be this problem, right? So how do we calculate this? So here we're going to use our first golden equation, right? What does our first golden equation say? F equals, so yeah, our first golden equation says that F is equal to, QE. And then this is why the golden equations are super important. Typically, this would be a difficult problem, but if you look at this, we literally just plug in values, and then we get our answer, right? So now we have that force, the charge is equal to 100 microcoulombs, right? So this is 100 times 10 to the negative 6 actual coulombs, right? And then multiplied by the electric field, right? Multiplied by 300 newtons per coulomb, which is our electric field. And then if we simplify this, right, this essentially means, yeah, if we simplify this, we can cancel out the 4 zeros with the 10 to the negative 6. So this will become 3 times, let's avoid using scientific notation here. So this would become 0.03 newtons, right? That's our force. So this is the amount of force required to push this 100 microcoulomb charge over this electric field of 300 newtons per coulomb. And notice here, we don't have to use any distance. It's going to be a constant force required to push it through a distance. Because remember, this electric field is the electric field between the 2 points. So as we increase the distance, there's going to be essentially less, there's going to be more electric field as we increase the distance. Now let's do a third problem. We'll stick with our point example because I like using the point examples for this. So let's say we have 2 points, right? Point A, point B, right? And then just to keep with consistency from last time, let's bring back that point A is 300 volts, point B is 100 volts, right? So now we have to calculate using this, right? Let's say that the distance between A and B, actually, how would I want to phrase this problem? Actually, let's actually phrase this different. So, yeah. So instead of doing this, let's say, okay, we have two, instead of potential, actually, let's say this. We have a 300 coulomb charge and a 100 coulomb charge here, right? That is separated by a distance of 2 nanometers, right? So what would be the potential energy difference? What would be the potential energy between these 2 point charges? So as you can see here, whenever we have like potential, electric field, force between 2 charges, anything like that, that's a sign we have to use Coulomb's law. So instead, our third equation, right? So we will be using, because it's electric potential energy between the 2, we will be using the variation with electric potential energy, right? So electric potential energy is in units of joules, which is Newton meters. So we have to take the original Coulomb's law equation, right? And everything remains the same, except we remove 1 r from the denominator, which will essentially make up for that m that we lost in the force. So this is our equation for the electric potential energy. And with this, let's assume the K is 9 times 10 to the 12, right? So 9 times 10 to the 12 Newton squared divided by Coulomb squared. So yeah, so now all we have to do here is once again plug in values. So electric potential energy will be equal to 9 times 10 to the 12 multiplied by 300 multiplied by 100 divided by 2 times 10 to the negative 6 meters. And you can already tell that the electric potential energy between these 2 is going to be pretty large, right? Because remember, we have 2 charges that are very high. They're like 300 coulombs and 100 coulombs are super high charges. And they are literally they're literally hair of a distance away from each other. So we can expect this number to be very huge. So as you can see, when we simplify this, we will get that the potential energy is equal to 27 over 2 times, if we add in all the zeros, this becomes 10 to the 22 joules, which is a heck ton of energy. So this helps tie with what we had before, which essentially states that, hey, if 2 charges are super big, then they will have a lot of potential energy between each other. And if 2 charges are extremely close together, they will also have a lot of potential energy between each other. So let's actually, before we move on, let's actually go through some AP questions, right? So, and it's very important that we do a lot of practice, because for physics especially, practice is extremely important. So we'll start. Let's start with this problem, right? So this is from the 2018 test, I believe, right? But actually, this will be AP 1, our first AP question. So this was essentially what they did is they gave you a graph, right? Like so. And there was essentially a curve, right? And this curve represents the this essentially represents the potential. This is a potential function, sorry. And then they gave you a couple of points, right? So they gave you a point here, right? This was, oh my god, dude. Point C. They gave you a point here, which was like point B. And they gave you a point here, which was like point A. And they asked you, in which of these points would this point charge experience the greatest force in the direction, right? So if we think about it, right, force in a direction, at least how we visualized it in the last lesson, was that the electric field is essentially the amount of like force that is being pushed on the charge, right? Either attracting it into a certain direction or repelling it in a certain direction. So in this case, it's clear we have to use electric field, right? And we're given electric potential energy. So in fact, we rely on our fourth equation we learned last time, right? So the fourth equation states that dV over dr equals to electric field. Negative dV dr equals to electric field. So in this case, we can easily tell because derivative is just the slopes. So essentially the one with the biggest negative slope will have the largest electric field. So, and this question asks specifically about the positive x direction. If it asks about the negative x direction, then we would look for the one with the biggest positive slope. But here it's the positive x direction, so it's the biggest negative slope. And in this case, we can see it's clearly A, right? C is a negative slope, but it's not as steep, and B is a very steep positive slope. So the answer to this question would be A. And remember, if you watched our last video and you went into this AP test, you would have nailed this question within like 30 seconds. This is like a 30-second question. So, yeah. And then essentially later, there was an extension of this question, right? Where we basically introduced a couple new points, right? There's point D here and point E here. And then, yeah. So for this, what it asked is at which of the points would the charge experience no force? So essentially this is using our same fourth equation, right? But this time we're asking where the electric field is 0 or the slope is 0. And this is very clearly at point D, right? Point C and point E do look like they're about 0, but they are very tiny. Like C is very tiny negative, so it's pushing it a little small amount in the positive x direction. And E is a slight positive slope, so it's shifting it slightly in the negative x direction. So the answer for this one would be D. So now let's get on to the actual lesson, because we've done plenty of review. But if you want more review, if this still doesn't make sense, then So if it still doesn't make sense, be sure to check out our homework speed-math-cs math-cs.glitch.me. It'll be the top link in the description, right? We have tons of practice problems on there, and this is also like the video for all of our classes. So there'll be practice problems on this lesson as well if it doesn't make sense. So be sure to check those out, since physics, like I mentioned before, requires a lot of practice. So now let's get into the actual infinite charge distributions, right? So like I mentioned at the start of the lesson, right, we are going to be using integrals, very obviously, to solve for infinite charge distributions. So let's start off with electric field. So essentially electric field, right, we're going to be using let's start off with the vector form of Coulomb's law, right? So this is essentially force if it was a vector, so like so. So this would be equal to the Coulomb constant times Q1, Q2 divided by R squared, right? And yeah, so this is the vector form of Coulomb's law. So now to convert this to electric field, what we have to do is we take the idea, we will actually do a little conceptual thought for this, right? So force is essentially if we have two charges here and here, A and B, what is the force that is being attracted between the two, right? Or being repelled between the two. So this is what Coulomb's law is telling us, right? For electric field, we essentially are just looking at this point A, and we're seeing, oh, if we placed a teeny tiny test charge in here, right? Teeny tiny test charge in here, what would its force be? So essentially what we do here is to convert it to the electric field, right? Yeah, so to go from force to electric field, essentially what we'll do is we'll take so remember that force is equal to Q times E. So yeah, so this is we're gonna use our first golden equation to actually help derive this, right? So this is force equals to Q times E, which in this case, our Q is going to be the charge of that tiny test charge, right? Times E. So if we actually isolate E, we get that E is equal to our vector force, remember electric field is a vector, divided by charge. So what we're gonna do is we're gonna take our Coulomb's law, right? Force as a vector equals to Coulomb's constant times Q1 times Q2 divided by R squared, right? So then if we go to electric field, right? Electric field is equal to force divided by charge, which is equal to the Coulomb constant times the test charge times the big charge divided by R squared Q, right? All of these cancel out, and then we have our electric field in vector. We have our electric field in vector form. So now, with this, let's consider if this was differential like electric fields and differential forces, right? This would essentially be like, hey, if we, the whiteboard can be super laggy sometimes. So yeah, dE, it would be equal to the Coulomb constant times dQ, right? Yeah, dQ divided by R squared. And now if we took the integral of this, right? If we took a nice integral, right? The integral of dE equals to the integral K dQ divided by R squared, right? Then we would get that electric field in a certain direction equals to, we can take this constant out, right? The Coulomb constant out is equal to dQ over R squared. So it's immediately clear that in order to simplify anything with this equation, we are gonna have to somehow convert this dQ over R into a dr, right? This is going to somehow have to convert into a dr. Because if you think about it, R, at least in our case, isn't even a constant. So we can't just take the R out. But also, our variable that we're considering is not even R, it's Q. So we have to find some way, in order to solve this, we have to somehow convert this into a dr. And in order to do this, we'll start with our first fundamental concept of today. And this will be a thing that we call charge density. So there will be three different types of charge density, right? Each one having a different symbol. So the first one is going to be represented with a lambda, right? This is the linear charge density. This will be equal to charge divided by length. And I say charge density because if you think about it, the amount of charge over length, right? So so like if there's a lot of charge in a small area, then we would say the density of charge is very high. So now we will do our surface charge density, right? Which is equal to charge divided by area, right? So this is essentially, we'll just do 1D, 2D, and 3D essentially. This is what this is. So, and then lastly, we will use the Greek rho, which is equal to Q over, charge divided by volume. So these are our three charge densities. So of course, it should be obvious that the linear charge density is in coulombs per meter, right? Because length is in meters, and the surface charge density is in coulombs per meter squared because the area is in meters squared. And lastly, for the volumetric charge density, it will be in coulombs divided by meters deep. Sorry, that took long. So now what you'll have to do is you will essentially have to substitute a linear charge density into it. And it'll depend on which shape you are using, right? So actually, before we do that, remember we can actually convert this into a differential, right? Just so we can substitute dq in, right? So for example, if we're thinking of length, right, which is what we were using from earlier, right? We take this length one down here. So we'll say that charge density times length is equal to charge. So then we can say that charge density times dl is equal to dq, right? And then using this charge density, what we will do is that up here, I'll bring this up here. This electric field vector will essentially be equal to this. Oh my god, such a messy integral. So times linear charge density times dr. Remember, we're not using L in this case, we're using R as a variable, so we'll do that, over R squared, right? So if we have something like this, we can take out, like, linear charge density will be a constant, take this out, right? And we will essentially have this dr over R squared, right? And this is a pretty simple integral to figure out at this point. This is just negative charge density divided by distance, right? So this is a formula in a sense, but like there's no need to write this down, as we're going to do a couple practice problems on this, right? But essentially you'll see, right, that this is actually an unwanted variable. We don't want it, right? So essentially what you'll want to do is, in the first place, like in this case we just assume like the electric field is something, but you'll want to find the differential electric field due to like a differential region. And you can essentially use the equation we derived from earlier, right? For Coulomb's law, use Coulomb's law to essentially like find a differential related to that. And then you want to integrate just like we did, right? Using like the geometry of the situation to find like the limits of the integral. Like for example, in this case, right, we're using linear charge density. So if we were trying to evaluate the electric field at a point in like a rod, that is for example distance A to distance B, then it's clear that we should bound the integral with distance A and distance B. So essentially this formula is actually invalid. I don't know why I put this. So yeah, that formula is invalid. But essentially you would use like sort of the geometry of the situation to find your bounds to the integral. And then the thing is, right, this is like a pesky variable that we introduced, right? This has literally zero meaning in the final value. So we are gonna have to find some way to get rid of it. So in order to do that, right, if you have like a constant, like for example, if you have like a plate, like the problem is the sense if it gives you a plate, right? Let's say it's a circle with a radius of 4 meters and like the whole charge is like 2 coulombs, like positive 2 coulombs. You can apply the charge density formulas that we used earlier, right? And on the homework, yeah, we have plenty practicing how to calculate this charge density. So you can do that. But the other way is, and this is in the problem, right? This is the second case, and this is super easy. And there will be a formula for linear charge density, right? Which in this case, you can just plug it in, and then you're like fine. So then, when you get your final result, make sure to check the units. If the units do not match up, you got the problem wrong. And this is especially important in FRQs. I'll state this multiple times, right? FRQs always build up on each other. You make one mistake, it propagates throughout the entire problem, and boom, you have a 0 on the FRQ, which is not good, right? Always make sure you check units. Unit analysis is the easiest way to check your answers. And of course, after you recheck your answers, recheck all your work, make sure you did it correctly. Also, make sure that logically it makes sense. I know it's especially for electricity and magnetism, it is harder to do that because in mechanics, you can relate it in real life. Like if you think of a ball bouncing, but you're like, okay, it'll only bounce point 0.0005 of the original height. That's not true. So you'll be like, oh, okay, my answer's wrong. But it's harder to do that for electricity and magnetism. But just think. For example, if in the earlier practice problem we discovered today, right? Let's say the charges were super big and the distance was super small and you got some crazy small potential energy. You will know instantly that you made a sign error somewhere. Because if the charges are super big, distance is super small, electric potential energy should be huge, ginormous. Because you put two charges literally right next to each other. There's so much potential energy there. So that is essentially you want to always check your units and check your answer just to make sure it seems good. So now based off of what we learned, right? This is actually fairly simple stuff, right? It is essentially just integral building. So now let's do a practice problem, right? So let's determine the electric field at a point. So let's say we have a point P. I'll use P for this one. Should make it a capital P, right? What is the electric field at point P, where we have we have a rod here. A rod of charge positive Q, right? So positive Q charge, positive Q all the way throughout. We have positive Q charge, right? And then the distance here was A. Yeah, the distance, sorry, I'm gonna put this in different colors so it's easier to see. Distance here is A, and the length of the rod is L, right? Yeah. So what would the electric field at point P be? So now let's take our let's take our equation from earlier, right? So d E, right, equals to, K times dq divided by r squared, right? That is our equation, right? And now if we take the integral of this, right, we will get that the integral of dE equals to integral of k dq over r squared, right? And for this, we will say, actually, let's put it in a different color. Red's kind of hard to see. So the electric field as a vector will be equal to the Coulomb constant times dq over r squared, right? You'll see we're at the same point in the derivation of this equation where we have reached a point where we need to substitute this for dr. So in this case, we will, for now, substitute this with, because the rod is linearly symmetric, we will say this is linear charge density times dr. And as for the bounds, we will say for now that essentially, if you think about it, right, we'll define these 2 points from now. We'll simplify this later, but let's define 2 points, right? Point A here and point B here, right? And essentially, let's say that these are the 2 points. So these are pretty obviously the bounds for the integral, right? So they're bounded by A and B, and bounds from A to B with this. So then essentially now we can simplify this integral, right? And we can say that this is equal to K, and because this is dr, right, this will be -1 charge density over R from A to B, right? Oh shoot, my battery's really low. I'll be right back. Okay, sorry. Yeah, I had to get my charger real quick. Yeah, so essentially for this, we would simplify this to negative charge density K times -1 over B plus 1 over A. And this will look like a completed solution, but come on, look at this. We've introduced so many random variables like linear charge density, A, B, like none of these were in the original problem. So we have to actually solve for each one of these variables, right? So Coulomb's constant, we know that's a constant. So this 9 times 10 to the 12, right? So we don't have to simplify that. But for this, right, we'll calculate each one of these, right? So let's start off with A. A is pretty simple, right? A is simply just the distance A from the point P. And then point B, right, was at the end of the rod. So this will be A plus L. And then linear charge density here will essentially be equal to the charge, which is positive Q divided by length, right, and L. So now what we would do here is we would simply like simplify all of this, right? Now we have positive Q times K divided by length times 1 over A minus 1 over A plus L. And there we go. That looks much nicer. It's using all the variables we used in our original problem. So now we would apply something similar for various other problems, but just for a quick problem, let's do a second problem. Actually, yeah, I think we can do a second problem. So we can do a second problem. So for the second problem, right, let's say we have a ring like this. A ring of charge, right, of plus Q, right? And then we'll actually define an axis right here. So there'll be an axis coming out of this. And remember, this is a ring. So there's nothing in between. It's just a ring around this point, right? And let's now say that this is essentially this right here. This distance is essentially A. Let's say that's our distance, right? Or radius is A, right? And let's say we have another point P along this axis that passes through the center, right? And then let's say this is a distance B from this ring, right? What would be the electric field generated by this ring up onto this point? So let's do the same formula from earlier, right? Where we would have dq divided by dq divided by, I don't know, why am I doing dq? I'm stupid. De as a vector equals to dq times Coulomb constant divided by r squared, right? And for this, we take the integrals once again. This will be E times the Coulomb constant comes out, integral dq over r squared, right? And we are back to the same place. We are back to the same place as before. So for this, what we have to do now is we have to do a couple things, right? Convert this to r, and then now find the bounds of our integral. So So in this case, right, if we think about it, we don't actually have to find any bounds for this integral because everything is just a set distance away. So if you think about it, right, you might be tempted, based on this rate, you might be tempted to think the bounds are like 0 to like 2 pi a, right? But remember, this integral will be based off of the distance r, and the distance r never changes. This is very important. The distance r, if the distance r never changes, we don't have to find bounds for this integral. So essentially, now what we will do is our process has been simplified like super a lot. So now we can just convert this into, once again, linear charge density times dr. So we can do the integrate. And at this point, we can just directly integrate. We don't have to worry about bounds, none of that. And this is why like rings of charge are my favorite things to see on AP tests. These are super easy to solve. This should be like a 1-minute job for you to just get done, move on. Rings of charge are super easy to solve for. So essentially So the electric field will be equal to this Coulomb constant, right? Charge density times K, right? The integral of 1 over r squared, remember that's negative 1 over r. This time we have no bounds, nothing pesky to worry about, right? Or actually, we've introduced once again this pesky lambda variable, so we have to remove that. So, and also this r, right? This r is not in the problem, so we have to get rid of both of these. So for this, right, what we will do is we'll essentially say, hey, we'll start off with the linear charge density. So this is equal to the charge, which is once again positive q, divided by the length. And the length is where we use our 2 pi a. That is our length. And yeah. So now for the distance r, right? If we go back to the original problem, we'll see that we can draw sort of a Pythagorean here, right? Going from here to here, right? We'll draw like a Pythagorean like that, and that will be our distance. So this is equal to root a squared plus b squared by Pythagorean theorem, right? So for that, we can simply plug that in, right? So e squared, or what am I saying? E squared. E will be equal to lambda. Or no, why am I? No, there's no lambda. Oh my god. Yeah. So this will be equal to positive q times k divided by 2 pi a. Well, actually, yeah, this will be negative now. So this will be negative because remember we have negative 1 over r, right? Negative over a squared plus b squared. So this is our potential, like from a ring. So as you can see, solving the ring problems are super simple. So this is the idea of infinite charge distributions. And of course, for potential, it's a very similar application. Instead use dV instead of dE. So that concludes my review of AP Physics C Electricity and Magnetism, infinite charge distributions, and charge density. So there will be homework and practice to go practice all this. Tons of problems regarding charge density and continuous charge distributions. So be sure to check those out. And I will see you in the next one.